And we're back in the studio. Thank you for staying with us. And now we're going to have the final talk for today. Very interesting one. Let's welcome our next speaker, Foad Shahbazi, the Network Operations Manager at Niantic. And do we have him here now? Yes, we do. Hello, Foad.
Good. How are you?
Can you hear me?
Yes, I can. Can you hear me?
Yeah, very well. How are you doing?
Good. Thank you. How are you?
Where are you based?
San Francisco.
San Francisco. Wow. So what time is it over there now?
It is 10:46 a.m.
So not that bad. Cool. Thank you very much for joining us in this London studio. Very excited to have you here. Yep. And
thank you.
All yours. Good luck.
All right. Cool. Good afternoon, everyone. Thank you for taking the time to join the session, which I believe is the last one for the day. I'm Foad, Network Operations Manager at Niantic, an augmented reality platform and mobile gaming developer here in San Francisco. And for the next 30 minutes or so, I will be talking about 5G, one of the most exciting developments in mobile technology and its features, which I believe has the potential to revolutionize the way we interact with the world around us, especially for gaming industry. So in this introductory presentation, we start with understanding the motivation behind 5G by reviewing the use cases and performance targets, and then compare those with what we are seeing today from 4G. After that, we will go over the key features of 5G air interface, including spectrum, bandwidth, and antennas. We will then take a look at 5G core and its major architecture enhancements in multi-access edge computing and network slicing. And finally, we'll review 5G deployments and the roadmap. So what is the motivation behind 5G? Why 4G is not enough anymore? Is 5G a needed upgrade or just marketing tactics created by mobile carriers and manufacturers? Today, with 4G, we get high-speed internet connectivity. We can do video streaming, we can watch live TV, we can run endless applications that we have downloaded on our devices on daily basis. But as we added all these new devices and application to the network, we created a huge problem with network congestion. In most countries today, the number of active mobile connections are more than the actual population, leading to this significant drop in quality of services such as speeds and signal availability. This by itself is an indication that 4G has reached its technical limits. There are three usage scenarios associated with 5G requirements, which you can see here. They form the points of this triangle known as 5G triangle. First, there is enhanced mobile broadband, or EMBB. This use case focuses on area traffic capacity and higher data rate. EMBB is the answer to cloud gaming and high-quality video streaming applications that require large file transfers and real-time connectivity. Second, there is ultra-reliable and low-latency communications, or URLLC. Applications in this scenario depend on millisecond latency and extremely low rate error rate, such as remote surgery or autonomous driving. The third one, we have massive machine type communication, or MMTC. With MMTC, the Internet of Things is a real possibility now. Smart homes or smart cities with all their machine-to-machine type communications, which require a very high connection density will now be supported. But one thing to note here is that not all 5G applications would have to fit in only one or like all these three usage scenarios. A particular application might require a characteristics from one or more of them. For example, an augmented reality application will fall, as you can see here, will fall somewhere within the range of both eMBB and URLLC. And that's because AR applications require both high data rate and low latency. Now let's look at performance target requirements. Basically, there are, for 5G, the KPIs are a little different than 4G. And there are 6 main key performance indicators for 5G. First, there is cell peak data rate. This is the maximum data rate that could be reached if all resources of a cell site were dedicated to a single device. As you can see, 5G can potentially offer 20 times higher data rate than what we see from 4G. This is something that will help significantly with high quality gaming. Next one is connection density, which indicates the maximum number of connected devices in a given area. 5G is targeting 1 million devices per 1 square kilometer. This is 10 times higher than what 4G is supporting today. The next KPI is over-the-air latency. This is the time it takes for information to travel from sender to receiver. 5G is aiming for less than 1 millisecond latency. This is 10 times quicker than 4G. Another target is data rate at cell edge, which is basically the usability of signal at its weakest point. Like in 5G, users still can get up to 100 megabyte per second data rate at the edge of the coverage area. That's a pretty impressive measurement. Compare that to 4G, which there are no defined values of this KPI for 4G because the quality is not really usable at the edge. The next one is throughput. Throughput is the capacity of total traffic across a given area. 5G promises 10 gigabyte per second per connection. As you can see, that's 100 times higher than what 4G can achieve. The final target is mobility. That's the speed at which the device can travel, but still maintain the connectivity and the defined quality of service of the network. 5G is able to maintain its connectivity up to 500 kilometers per hour, which is just a little over 350 kilometers per hour of 4G. Again, these are very optimal performance targets for 5G. And similar to usage scenarios that we covered on previous slide, not every application needs to hit every performance target or exactly these optimal numbers. Let's talk about 5G air interface. The most essential component of telecommunication is spectrum. The electromagnetic spectrum includes everything from radio waves to X-rays, visible light, or microwaves, or basically all kinds of light. Cell phones use light to send and receive voice, data, images, and so on. Cellular technology operates on the radio wave portion of electromagnetic spectrum, which ranges from 3 kilohertz to 300 gigahertz, as you can see on this graph here. The 5G spectrum is consisted of 2 separate ranges. First one is low band and mid band spectrum below 6 gigahertz, which majority of it is pretty much the same frequency also used by 4G today. The second range, which is the new high band spectrum, also known as millimeter wave, is the main frequency for 5G, which is starting at 24 gigahertz. The millimeter wave is the widest spectrum bandwidth across this entire radio wave. What that means is basically now we have a huge chunk of spectrum that's never been used before. Now, there are some general rules and differences that we should know about high band frequencies versus low band frequencies. Low band frequencies have wider wavelengths. This enables signal to have a better penetration and to travel further and cover more ground. Lower frequencies are ideal for rural areas or places with like a heavier structure. The downside of lower frequency, however, is that they're slower, meaning less data can be transmitted through lower frequencies at any given time. At higher frequencies, we can transmit more information per second. Therefore, high frequencies are much faster, which makes them ideal for high density areas with lots of capacity demand. But high frequencies have trade-offs too. They have smaller wavelengths, which translates to shorter propagation. Also, high frequencies are more sensitive to environment and obstacles. For example, the 5G millimeter wave, which is a very high frequency band, can be blocked by rain or fog, or even our bodies can block the signal, which is why 5G is going to require way more antennas to be deployed in comparison to 4G to cover the same given area. We discussed spectrum and frequencies. Now let's look at channel bandwidth associated with different frequencies and see what they mean for end user. Think of a frequency channel as a pipe. So the size of the pipe determines how much data can flow through. High frequency spectrum like 5G offers large channel bandwidth because there is much more spectrum that can be allocated. In 4G, as you can see on this slide, the maximum channel bandwidth was 20 megahertz. Basically, that was the size of the largest pipe for 4G. But the largest channel bandwidth for 5G is 400 megahertz. That's literally 20 times more bandwidth than can be allocated, which obviously translates to a significant like data rates and the speeds for the end user. Besides providing much higher data rate and much higher speed, another very important characteristic of 5G spectrum is improving latency. At higher frequencies, we can transmit the same amount of data in shorter amount of time compared to lower frequencies. And this is because the frequency channels are subdivided into individual data streams called subcarriers. The larger pipe in 5G provides a greater flexibility for the spacing between these subcarriers. In data transmission, the larger the separation between subcarriers, the less time it takes to transmit the same amount of data. In another word, we can transmit more slots in the same amount of time compared to 4G. Now, one thing to note here again is that most of today's 5G deployments are utilizing lower frequencies, and mainly because of two reasons. One, since 5G penetration is very small at the moment, mobile carriers are more focused on the coverage aspect of it than capacity. Number two, not all mobile operators have access to millimeter wave frequency of 5G at the moment, because that's the spectrum that obviously it's a new spectrum, and which have to be auctioned and then purchased. This will be an expensive investment by carriers, which have to happen over the years. So it's going to take some time. Massive MIMO. Earlier, we discovered that 5G millimeter wave spectrum has smaller wavelengths. Since antenna sizes are directly proportional to the wavelengths, a smaller wavelengths means smaller antennas. This is why 5G antenna elements are much smaller than 4G. As a result, we can group together many smaller antennas into a smaller space in order to implement techniques such as MIMO. So what's MIMO? Multi-input, multi-output technique. Basically, this is the ability to reuse the same frequency for multiple users. The benefits of MIMO are one, more users can simultaneously connect to the network and increase their overall throughput experience at the same time. But the major benefit of a smaller antenna element is something called beamforming technique, which is essentially aiming a lot of smaller signals at users instead of one large signal. Imagine a large flashlight compared to several smaller laser lights. You can get the same amount of light, but focused on where it is really needed. We can apply the same exact analogy with 5G spectrum, as it is shown on this slide. Imagine each laser light is now a radio beam. Using lots of different antennas, we can form individual beams that focus their energies to a specific user at a specific location. Also, because we are broadcasting signal in a specific direction, beamforming can reduce the interference, which was experienced by users who used to fight for the best signal all the time. This obviously is going to lead to a much better signal quality. Another benefit of beamforming is that it can potentially help with devices' battery life. See, when you have poor signals, the antennas inside your devices are constantly searching for the best or strongest signal. But with beamforming, since devices are going to receive their kind of own dedicated data stream, they now have to spend much less energy communicating to the signal source, which is the tower. Therefore, they're going to save their batteries. So to summarize, with MIMO and beamforming techniques, we can significantly improve user experience by allocating stronger and more cleaner signal, and also increase efficiency and overall data capacity by reusing the same available or existing frequencies. 5G core. Now we are going to look into 5G core and the introduction of two very important components of its architecture. Let's just start with multi-access edge computing. Edge computing refers to a design that moves computing and data storage out of the centralized clouds and bring them closer to the source of data. But what's the actual purpose of edge computing? Um, in in 4G, we use traditional client-server model, where all network functions are running on a centralized core, which could be 1,000 miles away from the actual client. So this long physical distance between the client and the server is obviously adding considerable delays to the processing time. But these kind of delays are not going to be acceptable if our goal is to integrate applications such as augmented reality, connected cars, or remote surgeries into our day-to-day life with 5G. So we had to find a way to reduce these delays. And multi-access edge computing is the answer. But you might be actually asking that, okay, we learned earlier that 5G can achieve less than 1 millisecond of latency. So what's the problem? Didn't we solve the delay issue already? Well, not entirely, because that 1 millisecond, that's over the air latency, which is from your device to the radio access, the signal source, which is the tower. It does not account for the end-to-end latency, including network transmission to the application server and back and forth. But thanks to the complete software-based 5G core, we now have the capability to bring computing and data processing functions closer to mobile devices by placing these virtualized servers right at the edge of the network. This way, data doesn't have to spend the time to travel all the way across the fiber network to a centralized cloud. Instead, all the data analysis and processes and the storage can be done at the closest MEC, multi-access edge computing, to where the user is. Let's use video game as an example. With MEC, the gaming session on player's device can immediately start talking to the gaming server that is local to the player instead of a far distance somewhere in the cloud. Also, with MEC, we can store cached information such as software or videos in the MEC platform closer to where the user is so that they can load faster. This allocation of resources closer to the user will obviously allows for shorter latency, which translates to a much better user experience at the end. As for game developers such as Niantic, we need to identify features of our games and applications that require this real-time response and processing at the edge, and then design them in a way that can support and launch the appropriate software in the MEC server. Basically, build MEC-ready applications that can fully benefit from this network design. So now let's talk about another key feature of 5G core, network slicing. So what is network slicing? It's an architecture that creates a customized logical network while sharing the same exact physical resources. So basically allowing multiple virtual networks to be created on top of a shared physical infrastructure. And this concept it's nothing new. It's very similar to what we already do with VPN, where a group of users are sharing the same sets of resources which are separated by administrations or security. Traditionally, mobile carriers have offered this best effort approach to every device and service. But but we now know that different services obviously have different needs. For example, in augmented reality gaming applications, without a low latency, it wouldn't be possible to meet players' real-time gaming demands. So we needed a mechanism that can isolate or allocate resources for a specific scenario. And that's exactly what network slicing will do for us. By dividing network resources to different slices based on users' demand and type of services that they request, whether it is speed, latency, capacity, coverage, security, and so on. Let's look at a real gaming example. Say a group of us, we are playing Pokemon Go at Golden Gate Park here in San Francisco. The first requirement in order to have a seamless Pokemon Go AR game experience is low latency. With network slicing, the 5G network can allocate resources to create this logical layer that caters to the specific need of us as a Pokemon Go players, which in this particular example is low latency. Now, let's assume there are some famous influencers in the crowd as well, who are trying to establish a live broadcast with their followers simultaneously. This is obviously an activity that requires a large bandwidth, right? This can also be solved by creating another network slice in a form of EMBB, which is going to provide a high data rate that these influencers need across the park. And the way that the network knows which slice to use is through what's called access and mobility management function, which it's responsible for understanding what the mobile device wants and then take it to the appropriate network functions. Keep in mind that all these network slices, and as you can see on this diagram here, they can coexist on the same set of physical and virtual resources, which can be reused over and over for many different service requirements. 5G deployment. So we talked about 5G air interface, we talked about core components. Let's see how we are going to deploy these elements in real world. In order to build a 5G network, we have to have a 5G radio access, 5G radio node, and an entire 5G core. So altogether, they make a complete 5G network, which we call a standalone 5G network. So when you hear the term standalone, that refers to an all 5G network. That's a layout you see at the bottom. But building a standalone network is going to take some time, and we are not quite there yet. But the telecommunication industry, they thought of an alternative way. For the purpose of faster 5G deployments and take advantage of its features, mobile carriers, they have created a new approach, which is the layout you see on the top. In this option, we first add the 5G radio equipment and then integrate them into our existing 4G core system over the traditional network connection. We call this approach a non-standalone network. This way, both 4G and 5G radios are co-located and deployed together, which gives the devices the option to communicate to both technologies at the same time through what's called multi-radio dual connectivity. When 4G and 5G networks are available to your device, obviously they are providing users with additional bandwidth because you're using 4G frequencies and 5G on top of that. So if your device is capable of both, then you have much higher bandwidth. Using the non-standalone design, we can already utilize some of the 5G use cases that we talked about to a certain degree, relying on 4G core. But when 5G core is ready, we will eventually add that to this mix, and at which point we can start removing the 5G core and base station slowly over time, which would leave us with all the standalone 5G network that we talked about. And finally, let's look at a high-level 5G deployment timeline. As you might already know, network operations began, operators, they began their 5G testing and deployment of their fixed broadband services back in 2018. Then the commercial mobile deployment in selective cities started in 2019, which has been continuing and reaching to more and more cities and locations since. We are now starting to see a more meaningful collaboration of 5G and other technologies, particularly virtual reality and augmented reality. But it's still a complete and fully 5G adoption probably won't happen until 2025. And that's because different organizations have different timeframes and strategies. So 5G implementation is not going to be a one-size-fits-all format. And of course, with the current state that we are in, and due to potential scheduling delays that mobile operators are facing because of COVID-19, these delivery dates might have to change slightly. There are, of course, some roadblocks that when it comes to the rate of 5G adoption between consumers and organizations. Main concern is obviously the availability. The lack of 5G services in certain areas may delay the adoption, or the belief that the existing infrastructure is not ready or cannot handle the technology can cause some hesitation. And of course, you always have the mindset of let's wait and see kind of personalities that can be a problem too. But most organizations recognize the need to invent, or at least to upgrade their existing products as part of the preparation for 5G arrival. At the end, no matter what the state of current 5G deployment is, we now know that 5G is here, and it's going to change the way we interact with our physical and virtual world. And that's very exciting, and I think we all should be looking forward to it. And that's all I had prepared
Thank you very much, Foad.
for
Thank
today.
you for your presentation, very detailed and very future looking for. Quick questions, if you don't mind.
Sure.
You've explained why the 5G actually will be beneficial to AR games. What about other games?
Definitely for every game. I mentioned AR because today, when you talk about AR, you need features like basically low latencies and very high data rates. That is something that 5G presents to you. But with every other games, even with normal games, which requires a high data capacity, and you need to have high data rates to be able to play seamlessly without any lag or any pause, 5G is going to help that as well. So any type of games that you have, and the other thing is 5G is going to kind of eliminate the need of having console, because now you have the freedom of playing any games at any locations that you are. You don't have to be at home connected to your Wi-Fi or your cable, because they provide you with a better, basically, internet connectivity. With 5G, anywhere you are, you have that, you can maintain that high quality connection. So there is no need of console or big TVs anymore.
Yeah, fair enough. Sounds like a dream future. And with your upcoming games, are you going to have it someplace released when the 5G is out, or what's the plan?
Say that again. I'm sorry.
I mean, with your games, will they be focused on more like 2023, 25 years? I mean,
no. So our games are basically, so our existing games are all AR capable, which can be
I don't know,
use 4G and 5G. But there are features within our games. For example, you're going to have arrays of multiplayer features that are going to take advantage of these 5G capabilities, which we are releasing next year.
Right, cool. Thank you very much for your presentation. It was fantastic to have you in the studio. Hopefully, it's something to you offline and learn more about the 5G thing. Thank you so much. It was fantastic to have you.
Looking forward to it.
Have a good day.